The topic for our last section in this unit is Riemann sums. Riemann sums are named after a mathematician who came up with the idea that we could start finding area underneath a curve by first working with rectangles. So we're going to mimic that approach. I have to confess that my handout is not the actual handout I wanted to give you. The numbers are a little different. When we get to each page, I will tell you what numbers that I want to work with. This first page, the topic is left-hand Riemann sums, and the directions in the left box tell us we're going to do a left-hand sum with, I wanted this to be a 2 with 2 sub-intervals, and then I wanted the number 5 to the right over here, this 2 sub-intervals, I wanted that to be 4. I wanted those numbers to be switched, and I think you'll see why when we do the math problem. Let's learn how to set up Riemann sums. We're going to use the graph to answer these questions. Number 1, sketch rectangles to approximate area under the curve for a left-hand sum. Now the request is that we do 2 subintervals, meaning we're going to do 2 rectangles, and we're going to place those rectangles on the interval from 0 to 4. So look up at the graph. Here's 0 all the way to 4. I'm going to fit 2 rectangles in that width. And so that means from 0 to 4, I'm going to fit a rectangle in here, and I'm going to fit a rectangle in here. Each rectangle will be 2 units wide. I'm going to use this x-axis from 0 to 2 as the base of a rectangle, and I'm going to raise that rectangle up. And that rectangle is going to go up so that it attaches to the curve on the left-hand side. That is what we mean by a left-hand sum. So raise the rectangle up, and it attaches on the left corner right there. We are about to find the area of that in just a moment. Let's first raise up the second rectangle because we want a total of 2 rectangles, also noted as subinterval. So I'm going to raise a rectangle up between 2 and 4. Raise it up until it attaches on the left-hand corner. So we'll find the area of this as well. Now, this is what is first thought of as area under the curve. And as you know, we found area under the curve in the last section, but the curve was nice. It was like flat and horizontal, and you could find exactly the area. Well, not every curve is flat and horizontal and easy. Some of them are shaped like this. This is a parabola. So we start off by doing this approximation. How good of an approximation is this? It's a pretty bad approximation, but that's so we can set up the idea, and then we're going to adjust the idea so that it's more appropriate. Okay, let's answer the question. The area of these rectangles, obviously the first rectangle has a base of 2, height of 1. The second rectangle has a base of 2 and a height of 3. By the way, I could have also put those additions together because they have the same base, so it's like I could factor the 2 out, and that would leave a 1 plus 3. So that's kind of a quicker way to do the math. You'll get 8 for the area. What do you think of this answer? It asks us in number 3, how does this approximation compare to the actual area under the curve? Well, you can see there's space still that we didn't account for. Like in here and in here, we didn't count that yellow part. Our answer is not a big enough number. Our answer is actually an underestimate of the actual area under the curve. So I'm simply going to write underestimate. Is this a good approximation? Absolutely not. There's too much blank area that we didn't calculate. So that's a bad approximation. Well, how do we do better? In number 5, I already asked you to change. Instead of 2 subintervals, let's go with 4 subintervals and see what that looks like. Now we're on the same interval. We're going from 0 to 4. I'm writing on the x-axis here, from 0 to 4. And instead of 2 rectangles this time, we're going to draw 4 rectangles. And they're going to be a left-hand rectangle. They're asking us for a left-hand sum. So we're going to raise the rectangles up until they touch the curve on the left corner. Since there's going to be 4 rectangles and we're going from 0 to 4, each of our rectangles will be 1 unit wide. The first rectangle is just actually this grid square right here, so this is nice. The next rectangle goes between 1 and 2. And when you raise up the rectangle there, you only get that far because the left-hand corner gets stuck under the curve. The third rectangle raises up between 2 and 3, and it can only get this far. The last one, the fourth rectangle, raises up and it attaches right there, about halfway between 5 and 6, okay? I think we covered more of the space under the curve. So this is better having more rectangles. The area of the rectangles can be found now. You can do each of them. You can do base times height. So 1 times 1 for the first rectangle. 1 times, I would say 1.5. So I'll put 1.5 there. 1 times 3. And 1 times 5.5. Now again, I want to encourage you to think about doing this easier, like set it up so it's easier. Each of these terms has a 1 in it, so the width of the rectangles can be factored out, and then just add the heights together. This will make your work much easier. If you calculate that, you should get 11. So that makes sense. We were thinking that the estimation on the left over here of 8 was kind of an underestimate and not very good. Well, now we see that the actual area under the curve is bigger, and 11 is our new estimate. Now 11 only takes care of these rectangles. There's still some space. So I'll use my yellow pen again. There's still yellow space here and here and here. Okay, it is not a great answer, the number 11, but it is better than 8. So that's an observation that we'll make, and then we'll improve our process as we go along. How does this approximation compare to the actual area? It is still an underestimate. That's a question you might have to answer. How does it compare to using 2 subintervals? This should be a 2 because the previous thing we did was we did 2 rectangles, not 4. How does it compare to the previous one? This is a better approximation. I want to work on this even more, and I'm going to do the same idea on this page, but the numbers are off. I like the 4 subintervals on the -4 to 0 interval, but on the right side, the interval is not the same. So change this interval to be the same, -4 up to 0. On the left side, number 9, we're going to do 4 rectangles for 4 subintervals, and then when we go on the right side, we'll do 8. So we will see the difference in our work and how accurate we are. We're going to sketch the rectangles on the interval from -4 to 0. So here's -4 on the x-axis, here's 0. And we want 4 rectangles. This time though, I'm still doing a left-hand sum. Look what happens when I raise a rectangle. They'll have a width of 1. When I raise it up and it attaches on the left-hand side, look at what happens. That first rectangle sticks out above the curve. Now the second rectangle with a left-hand sum is going to attach over here, sticking out above. So the left-hand sum on this side of the parabola is not the same kind of estimate. And then the last one right here. If we try to find the area of this rectangle, we're going to be doing 1 times 9. Remember how I'll factor out the width there? The second rectangle is 1 times 5.5. The third one is 1 times 3. And the last one is 1 times 1.5. When you do this calculation, you'll get 19. What would you say about this approximation? Is this an underestimate like it was on the last page? It is not an underestimate of the actual area. It's an overestimate because it's sticking out above the curve. So we've got too much area calculated up here. So this is called an overestimate. Comparing this result to our results for questions 3 and 7. Now remember, 3 asked us about our approximation. We had underestimates there. This one is an overestimate. So you can say that this is an overestimate because the rectangles are sticking out above the curve. Let's try to get an estimate of the same area from -4 to 0, but using 8 rectangles this time. So we're still going from -4 to 0, and that's only 4 units wide. So if we're going to put 8 rectangles in there, each of our rectangles will be half a unit wide. So the first one attaches on the curve up at 9. The next one attaches around 7.5. Third rectangle attaches at 5.5. Fourth rectangle attaches at 4. The next one is at 3. Oh, I think the next one is like 2.25. The next one's 1.5, about 1.25 for the last rectangle. You're going to have to find the area where the width is 1/2. So put a 1/2 out in front, and then you add up all of those heights. I'm getting 17.25. Don't forget to multiply by the 1/2 after you add up all those numbers. How does this approximation compare to the actual area under the curve? This is still an overestimate. The rectangles were sticking out above the curve. But number 16, is it a good approximation? At least it's better than using 4 rectangles or 4 subintervals. You see, right now in geometry, we can take our knowledge of area of rectangles, apply it to the situation where we don't really have rectangle shape. And that process, when we go from 4 rectangles to 8 rectangles, I know you would think next we're going to do 16 rectangles or 32 rectangles. That would get a bit cumbersome. But as we make the number of rectangles increase, the better our estimate of area will be. And that's where calculus comes in. If we want to add up a whole bunch of rectangles like that, a function in calculus that will allow us to add up a lot of rectangles. In fact, we can make the number of rectangles go to infinity. And when we do that, when we pretend the number of rectangles go to infinity, then we would get an exact area for under that curve. Let's look at what a right-hand Riemann sum would look like. So on the next page, this is activity 2, I'm going to do the 4 subintervals on the interval from 0 to 4, and then I want to do 8 subintervals on the interval from 0 to 4. Let's draw in 4 rectangles from 0 to 4. Here is our x-axis. From 0 to 4, we want 4 rectangles, but this time they're going to be right-hand rectangles. So when you raise up your rectangle, don't focus on the left side now, focus on the right side. You'll raise it up till the right side of the rectangle touches the curve. That's where your rectangle stops. The next rectangle is going to raise up till it hits this point on the curve and it will stop. The third rectangle goes all the way up to 5.5. And the last rectangle goes all the way up to 9. You know how to find area here, so we'll factor out 1 as our width, and it'll be 1.5 plus 3 plus 5.5 plus 9. So you should be getting 19 for that area. Can you designate this approximation as an underestimate or overestimate? Can you tell me if this is a good approximation? To get a better approximation, one thing you can do is increase the number of rectangles that you insert. So if we go with 8 rectangles and we're only on an interval from 0 to 4, that means our rectangles are going to have a width of 1/2. Raise them up so the right hand touches the curve. So there's a lot less of the rectangles sticking out above the curve. This estimate is going to be more accurate. They have a width of 1/2 and their heights are 1.25, 1.5, 2.25. I'm getting 16.875 as my approximation. So that is a lower number than 19, and we still have a little bit of the rectangle sticking out above the curve. So while this is still an overestimate, it is not a great estimate of the area. It is better than using 4 subintervals. On this next page, 9 through 16, I would like to look at 8 subintervals on the entire interval. So let's go from -4 to +4. And then we'll increase our number of rectangles when we do the second problem. So I'm going to ask you to pause the video, sketch your 8 rectangles from -4 to +4, and you're going to do it with right-hand rectangles. Calculate your area, and then do the same thing for 16 rectangles on the same interval from -4 to 4. So pause the video, do your drawing and your calculation, and then turn the video back on to check your answer. I think we're getting a better idea of what the actual area is under the curve by having so many rectangles. Did you notice when we did it this way, we had some rectangles that weren't quite making it all the way to the curve, so we had space between the rectangle and the curve, so it was like there was an underestimate happening on the left, but then there was an overestimate happening on the right. So that kind of cancels each other out. So I think around 30, or actually it's going to be a little less, under 30, is a very good approximation of area under the curve. That's as far as we're going to take it with the idea of area under the curve. We're not going to make you draw hundreds of rectangles, but now you have the starting idea of what's going to happen. This third activity and last activity lets you know that we could take the approach further. Instead of using rectangles, you might notice that trapezoids could be a better option. So we're going to practice with trapezoids a little bit since we know the area for trapezoids. Let's review that. The area of a trapezoid is 1/2 the height times the sum of the bases. To start off, we have a graph of the parabola again, and we're going to sketch trapezoids to approximate the area under the curve with 2 subintervals on 0 to 4. So this means 2 subintervals will be 2 trapezoids, and we're working on the interval from 0 to 4. So from 0 to 4, I have to fit 2 trapezoids in here. And a trapezoid is like a combination of a right-hand sum and a left-hand sum, because when I raise up my trapezoid now, I'm going to raise it up. Notice how the parallel sides are vertical. I'm attaching on the left and I'm attaching on the right. And the trapezoid is when you connect those 2 points. So here's the trapezoid for the first one. Now the second trapezoid is already attached on the left, and here I go. I'm moving the trapezoid parallel side, that's the parallel side, the base is going all the way up to here until I reach the curve, and then I connect those 2 points. Well, that connecting those 2 points is pretty close to the actual curve itself. That trapezoid fits that part of the curve great. So we're going to find the area of these trapezoids. 1/2 times the height. The height is how wide these trapezoids are. So this is height, and it is 2 in this math problem, times the sum of the bases. So here's base 1. It has a height of 1. It is 3 units long. Base 1 is 1 unit long. Base 2 is 3 units long. So I'm going to write 1 plus 3 for the sum of the bases. The bigger trapezoid has the same height of 2. The first base on that trapezoid has a length of 3, and the long base has a length of 9. Notice how each of those terms have the 1/2 in it, and the trapezoids are always going to have the same height. So you could factor out the 1/2 and the 2, and that leaves behind 1 plus 3 and 3 plus 9. So you could do that setup instead. It's shorter. The answer there is 16. Is this approximation close to the actual area under the curve? And I would say it's close. It's an overestimate, but it is close. And that's only 2 trapezoids that gave us a close estimate. If we tried to do the same thing down below, using 4 trapezoids this time, we would get a better answer. So go ahead and draw in the trapezoids and then do the calculation. So we're going from 0 to 4, and remember to attach on the left and on the right. 1/2 is in the formula for the trapezoids, and the 1 is the height. Remember this width here, that's the height of each trapezoid. It's going to be the same. So the height is 1 and the sum of the bases. So I'm just going to add all the bases up. The first base is a 1 and the next one is a 1.5. So this comes from the first trapezoid. The next trapezoid is 1.5 and 3. The next one is 3 and 5.5. The last one is 5.5 and 9. That sum is 15. And that's really good, 15. That's a very good approximation. Do you remember on the last page, our area going from -4 to +4 was about 30, and 15 is half of 30, and we're only doing half of the picture. So I think 15 is a great answer. And as it compares to using 2 subintervals, it's a better approximation. The more trapezoids we use, the better approximation we get. On the last page, we are going to actually do 7 through 9 with 3 subintervals. So change this 4 to a 3, and we're going to change our interval. We've been going from -4 to 4 this whole time, but let's try something different. Let's go from -2 to +4. And then when we go down to the next half of the page, we're going to do 6 subintervals instead of 3. So go ahead and do your drawing and do your calculation and see how it compares to this answer. So you could pause the video and then come back to see if your answers match with these.